Thank you a lot, Hilda. Can you hear me well? The volume is okay? Okay, so I start. First of all, I want to really thank the organizers, Hilda, whom I know since many, many years now, Francisco, Marcus, Roberto, and Yamir. And it's really a pity that I could not come there. I really wanted to come, but unexpected duties in Italy prevented me from being able to come to Brazil this time. So I'm really sorry for that, but I hope to see all of you very soon somewhere else. Today, I would like to center my talk on the transition to synchronization of network dynamical system. There are many, many reasons for this talk. The first is evidently that it fits very well in the general topic of the workshop, dynamical processes on complex networks. Synchronization is a dynamical process, and we are speaking of synchronization on complex networks. So, I mean, this is a good fit for the audience. The second reason is that this paper has been recently accepted finally after more than 1 year of fighting in Nature Communications, and I'm very, very proud of this because this talk is going to touch a series of points about synchronization starting from more than 20 years ago, which in a sense add some clarifications to many issues which along the years, including myself, were misunderstood. So I hope that in this case, we will make a sort of recap of this subject in a way that can clarify a series of issues. I have, of course, to thank also the other authors, I mean, my co-authors, which in this case is an international team. We have 3 people from Iran, Sayad, Miss Bayani, and Miss Nasarimeh. Then we have a fellow from Russia, Kirill. We have a lady from Chile, Karin, a fellow from UK, actually from Spain, but he's in UK, Ruben, and Gonzalo Contreras Aso is one of my students in Madrid. So let me skip a lot of things about the introduction. I imagine that you know very well that synchronization is an old problem in physics. It goes back to Christian Huygens. So you know all the story of synchronization. And you know very well that the reason why synchronization is studied in distributed systems is that this dynamical process is extremely important in the collective behavior, characterizing the normal and abnormal functioning of most natural systems and man-made systems, from brain dynamics to heart beating, animal behavior. Here you have flocking. People are guessing, I mean, that also synchronization play a role in world climate. And also in man-made systems, clapping, if you will like this talk, you will clap at the end. So it's a classic example of synchronization of a network of people. Internet, power grid, I don't know. I mean, there are many, many. So let's go to the point. The point is that we are now imagining to have a system which is formed by millions, a lot of units, and these units have an internal dynamics, and then these are coupled, these units, by means of some network, some complex architecture. And the interest is to study, I mean, how the structure, the property of the network influences the dynamics, the formation of synchronization, and many other things. So normally, when you study synchronization, you have a control parameter, which is generally taken to be the coupling strength in each link of the network, and you have an order parameter. parameter, which is, for example, in the case of Kuramoto oscillators, is the Kuramoto order parameter. In other cases, it's the synchronization index. In other cases, it's just correlation, whatever you want. It's a parameter which is measuring the order that you have in your system. And therefore, synchronization corresponds to a transition from one phase, which is a fully disordered phase, which happens when the control parameter is too small. This fully disordered state is to all extent similar to a Boltzmann gas. So it's a gas of particles, image very disordered. So this is the phase 0, where the order parameter is 0. And then you have instead a fully ordered phase at the end of the transition, when the coupling is sufficiently large. And this state is fully ordered. That is like a solid, okay? It's like a crystal. So all the matter is studying how the system passed from one phase, the gas, to the other phase, the solid. And there are basically two ways of doing so. Either the system experience a sort of first order like transition, that is, you increase the control parameter, the system is frozen in the gas phase up to a given point in which it jumps suddenly to the ordered phase, to the solid phase. And in the way back, because you can also start the system in the other phase, in the solid phase, and decrease the coupling parameter, you have another transition. Generally, it may be at the same point or at different points, so you may have hysteresis. But what is important here is that if your systems is like this, and this is what is called normally as explosive synchronization, it has been studied several times in several circumstances, the system has only these two phases. So you have only the gas phase, the solid phase, and you have transitions, abrupt transition from one phase to the other. And you have nothing in between. So as I said, this is called explosive synchronization. There is a lot of literature here, but I'm not going to speak of this case. I'm going to speak of the other case, which is the more, so to say, natural case, more frequent case, if you want, in which the transition is second order like, that is continuous. Therefore, you start from this zero phase, from this gas phase, and you increase slowly, okay, the order parameter up to getting the solid phase. It's continuous, is fully reversible in the sense that if you start from the solid phase, you go back, you make exactly the same transition line, and you have, therefore, a very large range of control parameter, this one in the middle, in which the phase of your system is not a gas nor a solid. It's something in between. Okay? And what is this something in between? This something in between is the presence of clusters. That is, you have group of nodes of your network which synchronize, form a synchronized cluster, and this synchronized cluster coexists with all the rest of the network which may be unsynchronized. So you have formation of one or two or three or many of such clusters, which are a group of nodes performing the same synchronous dynamics without being synchronous to the rest of the network. So this is a sort of cluster state. And what I'm going to describe today is exactly this. How can we predict these clusters? How can we describe these clusters? How can we predict exactly the time at which this cluster will be formed, will be stable? And how can we describe the entire transition, in the sense, the entire sequence of clusters that are being formed before the system actually gets the solid phase. Because you understand that this clustered state is really interesting. I mean, the gas, both the gas phase and the solid phase are very trivial. In one case, you have zero order. In the other case, you have the entire network, which practically behave as a single unit. But in this clustered state, instead, you have a lot of complexity because you have this cluster that merge, that may increase their size, and so on and so forth. So our talk today will be devoted to try understanding as much as we can of this transition. And in order to do this, we have to start from the very, very beginning. That is, from more than 20 years ago, when for the first time Lou Pecora and Tom Carroll proposed a way of assessing the stability of the solid phase, that is, of the solution where the entire network is synchronized. So we are considering a network of dynamical units. So each node I is a vector state xi. Then you have a flow fxi, which describes the evolution of each node in absence of any coupling. And then you have the coupling term, which can be written in many, many ways, but I prefer to write this because if I write in this way, I save more or less 4 or 5 slides of operations. But what I'm going to say is not limited to this form of coupling. Actually, what I can tell you, it's you can have any coupling, I mean, any function of the xj and xi variables, provided that they are synchronization non-invasive. That is, provided this function are 0 when the network is synchronized, when xi is equal to xj. Okay, so any function of 2 variables such that is 0 when the 2 variables are equal. One possibility is a diffusive coupling. So you have an output function h, and here you have diffusion of this output function. So you have the sum of the elements of the adjacency matrix, which describe the topology of the network, how the nodes are connected among them, times x, this function h at xj minus the function h at xi. Then sigma is a global control parameter, is our what was reported before in the horizontal axis. And then you can rewrite this in a simplest form by using the Laplacian matrix. So therefore, you have here the Laplacian metric Lxj of h of xj. So what Pecora and Carroll did, they simply noticed that the existence and the invariance of the synchronization solution, where all the nodes are equal in time, and which obeys S dot Fs, so there is no coupling, is warranted by the zero sum property of the Laplacian, and they decided to study the stability of the solution. Therefore, one considered perturbations of the form delta xi equal xi minus s, put down this perturbation, and write down the linearized equation for the delta xi. One obtains these equations, which, as you see, contains the Jacobian function of the function f, that is the Jacobian of the flow, and the Jacobian of the output function h. And then one can introduce this big vector delta x, which is delta x1, delta x2, delta x3, delta, all the delta, the overall deviation, and write in block form this equation in this way. That is, the derivative in time of this big vector is nothing but the identity matrix direct product with the Jacobian of f, calculated in the synchronized solution, minus sigma, the Laplacian direct product Jacobian of h, calculated in the synchronized solution. Then one can imagine, for example, the simplest case of a network which is undirected and is therefore symmetric, and therefore it's always diagonalizable. So the Laplacian has its own basis of eigenvectors. Moreover, the first eigenvalue is 0, and this is extremely important because this eigenvalue 0 has associated eigenvector 1, 1, 1, 1, 1. Therefore, it has as associated eigenvector exactly the synchronization manifold, the solution of the synchronous solution in the phase space. And one can therefore say, since they are providing a basis for Rn, what I have to do is to determine that this solution is stable. Therefore, the entire phase space should be contractive towards this solution. And this means that all the other direction corresponding to V2, Vn, to the other eigenvectors, must be contractive. So one writes this perturbation as a combination of these eigenvectors, writes therefore the equations for the coefficients xi of this expansion, and it obtains this equation, which is xi dot jfs, that is the Jacobian in the synchronized solution, minus sigma lambda I, because for each eigenvector vi we have the associated eigenvalue lambda I, jhs. So we have a core here, you see, that is, these equations are variational, that is xi dot is only function of xi, and the core is equal for all I except for the presence of the corresponding eigenvalue. So here the first idea by them was, let's then parameterize this equation. So we introduce a parameter nu, which is sigma lambda, and we study a unique parametric variational equation, xi dot jfs minus nu jhs xi, and for each value of nu, we calculate the maximum Lyapunov exponent associated to this equation. So the maximum Lyapunov exponent associated with this equation is the master stability function. And its meaning is very important because here, you see, you succeed to separate the dynamics from the structure. You know, what you have inside the brackets here, it's only dynamics. It depends on the flow, the Jacobian of the flow. It depends on the Jacobian of the output function. So you tell me which is the unit. Of course, I forgot since the very beginning to say that the hypothesis we are making is that all the units of the network are identical. They are identical. So you give me the specific dynamics which is taking place in each unit, maybe the Lorentz system, the Ressler system, the Kuramoto system, the Maxi-Glass system, whatever you want. You tell me how these systems are interacting, what is the output function through which they interact, and I can immediately draw this function without, and this function tells you the behavior of this system with respect to any possible network, because now each network, you see, corresponds to a specific set of eigenvalues of the Laplacian. So a specific set of points that you have in the x-axis of this function. So basically, you have a function, and you read this function only in the points which are corresponding to the specific eigenvalues of your Laplacian times the coupling strength. Okay, so I dedicated already 15 minutes to this, but it's very, very important to understand that this function allows a classification of networks in terms of their capacity of synchronization. I don't like to call ability of synchronization for something that we will see soon, but capacity for synchronization. So, first of all, imagine that your units are chaotic systems. So if your units are chaotic system, then the master stability function will start at nu equal to 0 with some positive value, because at nu equal to 0 means lambda equal to 0, and lambda equal to 0 means the synchronized solution. So here you have the maximum Lyapunov exponent of the single isolated system. And the single isolated system, if it is chaotic, it will be positive. Then you have only three possibilities for small lambda. So for small sigma, sorry, if you study the first transition to synchronization. The first is the so-called, well, here is called the three in our case is 1, 2, 3. Let me see. Let's do here, it's much better. So the first, so we start from a positive value. So the first possibility is class 1 systems. Class 1 systems are systems which the master stability function never crosses the x-axis. So look at the yellow curve. And this kind of systems defy intrinsically synchronization. Why? Because whatever network you will use, you will always read in any point in nu some positive value. So no matter how you connect these systems, you will never synchronize. So class 1 systems, problem finished. You don't have synchronization. You will never have synchronization for no matter which network you use in order to synchronize the system. So neither the synchronized solution nor any other cluster synchronized solution will ever be stable. It will be always unstable, because in the direction perpendicular to the synchronization manifold, you will have positive values of the Lyapunov exponents, the maximum Lyapunov exponent. Then you have class 2 systems. In class 2 systems, it's a blue line. You have one intersection with the x-axis. So you have nu star, and before nu star you are positive, and after nu star you are negative. But this you understand that these are the opposite of class 1, because these systems will always synchronize, provided that you can increase sufficiently the coupling strength. So no matter how you connect them, you have a condition such that the coupling strength, which is now D, times the second smallest eigenvalue of the Laplacian, should be larger than this point. Then the third will be here, the fourth, 5, and you will always have negative values in all possible directions perpendicular to the synchronization manifold. So class 2 systems are the opposite of class 1 in the sense that they can always synchronize. Of course, if you want to decrease the threshold for synchronization, you have to increase lambda 2, because the threshold for synchronization is D equal nu star, this value, which only depends on the dynamics, divided by D, lambda 2. So if you want to make a network which is synchronizing better, you increase lambda 2, the connectivity. Then you have class 3. Class 3 is a situation a little bit more complicated, in which you have this red line, and you have two intersections, nu 1 and nu 2, nu 1 star and nu 2 star. So now what you have to do, you have to have all the spectrum of the Laplacian multiplied by the same D inside this region, because this region is the only one where the curve is negative, and you want to have contraction. So you have two conditions. The first is that, again, d lambda 2 must be larger than this. But at the same time, for the same d lambda n must be smaller than this. Otherwise, the maximum eigenvalue of the Laplacian times d will exceed this threshold, and you will read a positive value. You will have at least a direction of the perpendicular to the synchronization manifold, which is unstable. So this condition means that now it depends very much on the network that you use. There may, given a system, you may have networks which allow synchronization of these systems, and network which does not allow synchronization of systems. Okay? This is important because it is, unfortunately, and this is the first thing, a lot of attention has been paid in the past to a concept of synchronizability. And And the concept of synchronizability was, in a sense, quantified by this ratio R, which is the ratio of lambda n divided lambda 2. That is the maximum divided by the second smallest eigenvalue of the Laplacian. And it was argued that this, which is by definition larger than 1, because you ordered the eigenvalues by size, the smaller is this ratio, the better is the synchronizability of the network. Unfortunately, I myself published 2 papers which use this concept and this measure. But the question is, does it really make sense? You see, this means if you want to compare networks, and in terms of their synchronizability, does it make sense? And you understand immediately that for class 1 systems, it is completely senseless, because if you take 2 networks of the system in class 1, you will not synchronize in one, you will not synchronize in the other. So what is the sense of measuring something that should tell how much is more synchronizable the first with respect to the second, since at the end you will never synchronize? But there is something even worse. For class 2 system, this concept can be even wrong, because the range of coupling strength for which you have synchronization, stable synchronization, is unbounded. And depends only on lambda 2, not on lambda n. So imagine to consider this counterexample. You take 2 networks, G1 and G2, and you have lambda 2 G1, 1, lambda n G1, 2. So lambda n divided lambda 2 is 2, 2 divided by 1. Then you take the second network and you have lambda 2, 10 to the 45, and lambda n, 10 to the 46. So lambda n divided lambda 2 is 10. So according to the criterion synchronizability, G1 is better than G2, because 2 is smaller than 10. But you understand that if you calculated the threshold condition for synchronization, the threshold for the second network is 45 order of magnitudes smaller than that for the first network. So it's a completely wrong statement, because you are taking more synchronizable something for which the threshold of synchronization is 45 order of magnitudes smaller, so it's larger. So you can imagine how wrong can it be. This has sense only for class 3 systems, and only for defining, for indicating the range of coupling strength for which you persist in the stable region. Okay? Now, given this, the second step you have to do is to understand that this is valid for the solid state. When you consider the cluster state, that is, group of nodes which are synchronous, but the rest of the network is not synchronous, you can easily demonstrate that the linearized equation for stability of this solution, which is now a solution limited to the nodes inside the cluster, is exactly identical to this. What changes is the solution, S. What changes is that these Jacobians, in order to calculate the maximum Lyapunov exponent, have now to be calculated in the synchronous solution of the cluster. And the synchronous solution of the cluster has a piece which is linked to other nodes in the network which are not synchronous. So, in a sense, this is a perturbed synchronous solution, okay? And in our paper, you can calculate exactly how much is the perturbation. And the idea now is, let's make a zero-order approximation. And the zero-order approximation is that the perturbation that is made on the cluster is very small. And therefore, I refer all the times the master stability function of the unique solution of the solid state. Okay? This, of course, is an approximation, because for each cluster, I will have to recalculate the maximal Lyapunov exponent, transverse the solution to the new solution, which is slightly different from this. Not really too much different from this, as we will see, as soon as the coupling strength is small and as soon as the clusters are sufficiently compact inside and not too much densely connected to the rest of the network. Now, if I can refer for each solution to the same master stability function, which I repeat is an approximation, I can now make a second step, which is let us now to unfold the transverse space. So I now have, of course, it does not make sense that I speak of class 1. I speak of class 2 and 3. So what happens now is, let me consider the transition to synchronization. So I will consider this threshold new star and this other new star 1. And anticipate that the transition is exactly the same, okay? For class 2 and class 3, with a small difference, but this is really a big detail. So what happens? I increase progressively my coupling strength from 0. So what happens that the eigenvalues, so let's now look class 2. The eigenvalue will pass this sequentially. So the first will be lambda n times some d. Then I increase d. Also lambda n plus 1, lambda n minus 1 will pass here. Then lambda n minus 2 pass here. Then lambda n minus 3. So what happens is that at each value of d, I can factorize the tangent space of my synchronous solution into the product of two subspaces. One, which is spanned by the eigenvectors whose eigenvalues are already here, times the one which is spanned eigenvector for which I'm here. So one contains only contractive directions here, and the other one contains only expanding direction, which are here. Okay, so this is the second case. So at each value of d, I will always have a subspace, which is the one having an orthonormal basis, the set of eigenvectors vi whose corresponding lambda I multiplied by d have already crossed the stability threshold, which is containing only contractive directions. Okay, this is the first observation. Second observation, and this is something that really I was not thinking a lot, but for a mathematician, this is a stupid thing, but for a physicist, you know, you need to think. If you normally consider the matrix V, where the eigenvectors are the column, the matrix, then you can demonstrate that the rows of this provide also an orthonormal basis. And this is because the columns are orthonormal by definition, and therefore you have that V times V transpose is the identity, which means that V transpose is V minus 1, because V minus 1 is also the identity. Therefore, the identity, you can write also V minus 1 V, it's also V transposed V. So you have that V transposed is equal to V transposed V. So which means that this matrix V commute with V transposed. But this, besides being a stupidity, it has an important consequence. And the important consequence is that you can examine the eigenvectors component-wise. That is, you can take one vector formed by the first components of the eigenvectors, a second vector formed by the second components of the eigenvectors, a third one formed by the third components of the eigenvectors, the nth one formed by the nth components of the eigenvector, and these vectors are providing to you an orthonormal basis. So let's now use this fact to construct a set of matrices. So for each one of the eigenvectors Vi, having components 1, 2, n, I introduce this E lambda I, which is nothing but the components of these vectors I and j compared and squared. So I have component 1 minus component 1 square, component 2 minus component 1 square, component 3 minus component 1 square, component n minus component 1 square. Second row, 1 minus 2, 2 minus 2, 3 minus 2, n minus 2. Finally, 1 minus n, 2 minus n, 3 minus n, n minus n. So what I'm doing is I'm taking these components of the eigenvectors and I am calculating the difference and squared. And then I construct the following sequence. So I take Sn plus 1, the zero matrix. Then Sn is equal to E lambda n. Then Sn minus 1 is equal to E lambda n plus E lambda n minus 1. Then I sum E lambda n minus 2. Then I sum E lambda n minus 3. So I sum this E lambda n in the same order in which the corresponding eigenvectors are passing the stability threshold. Remember, they are passing the stability threshold in the inverse order of the sides. So I'm summing up these vectors, these sequences, these matrices, in the same exact order. N, n minus 1, n minus 2, n minus 3, n minus 4, so at the end of the end, I will have S1, which is the sum of all E lambda I. Okay? And now look, question, which is the maximum entry of this E lambda I? The maximum entry of this E lambda I is 2 and corresponds to the fact that the two vectors are orthogonal. Why I'm speaking of two vectors? Because this Si, this matrices Xi, you see, the off-diagonal elements of these matrices are nothing but the square of the norm of the vector obtained as the difference between the one norm vectors defined by rho I and j of matrix V limited to the last components. So in order to have, I take rho I, rho j, these two vectors which are orthogonal, I remember to you, I limit them, I read only the last components, and then I move these last components up to the end, and I make just the difference square. So it's the norm. And therefore, the maximum norm I can have here is 2 when they are orthogonal. When they are orthogonal, this is norm 1, this is norm 1. In the middle, you have norm square root of 2, and square root 2 to the square, it's 2. So the maximum entry you can have here is 2. And by definition, if I read S1, which is the last in which I sum all the components, since this is an orthonormal basis, S1 will be 0, 0, 0, 0 in the diagonal, 2, 2, 2, 2, 2, 2, 2, 2 everywhere else. Because no matter which ij I'm taking, they will be orthogonal when I consider all their components. And now let's make the definite and fundamental step, which is step 3. In order to make step 3, I need to define what is a localized spectral block. Allora, a localized spectral block is defined in the following way. A subset S, I1, Ik, so it corresponds to k indices, consisting of k minus 1 eigenvectors of the Laplacian, forms a spectral block localized at nodes I1, Ik, so indices I1, Ik, if each eigenvector belonging to the set has all entries except I1, Ik equal to 0. So it's localized in the sense that all the components of the eigenvector except those ones are 0. And all the other eigenvectors which do not belong to the subset have the entries I1, Ik, all equal, because they need to be orthogonal when you make the scalar product. Now, you can demonstrate the following theorem, which is what we have done in our paper. And the theorem says the following. The two following statements are equivalent. So if and only if. Statement number 1, all k nodes belonging to a given cluster, defined by the indices I1, Ik, have the same connections with the same weights with all other nodes of the network. So all other nodes that do not belong to the cluster. Which implies that for any pair of indices PQ inside this set and any index J outside this set, the entry of the Laplacian Pj must be equal to the entry of the Laplacian Pj. This means that these specific k nodes are indistinguishable to the eyes of any other node in the network. They receive the same input, whatever is the dynamics of the network. And therefore, since they receive the same input, they are potentially synchronizable, independently on the rest of the network. So this statement number 1 is equivalent to statement number 2. There is a spectral block Si1, Ik made of k-1 Laplacian eigenvectors, which is localized in the nodes I1, Ik. So this really closed everything, because now I don't enter into the consequence. There are many consequences. This is different from a symmetry orbit, because a symmetry implies a permutation, and this condition, statement number 1, only implies a condition on the link between the member of the cluster and the rest of the network. But it does not imply any condition inside the cluster. So you can have any structure inside the cluster. Motifs can be particular. I mean, there is a lot of things to do here. And also, this is slightly different from an equitable partition, because you need this, what is called external equitable partition. Okay. So what I'm saying conceptually, the nodes belonging to a given cluster are indistinguishable to the eyes of any other node of the network. They receive the equal input, so it's a dynamical equitability, or it's a structure equitability. And therefore, for the principle that the same input will eventually imply a same output, they may synchronize independently on the synchronization property of the rest of the graph. Let's cook the cake. I don't want to enter, maybe if there are questions at the end. So, the idea is, if they synchronize, it means that there is a spectral localized block. But if there is a spectral localized block, it means that some of these matrices will have 2 before S1. So before summing all components, when I sum all the components up to that point, I will already be completely orthogonal. The specific nodes will be completely orthogonal. And therefore, I will form a subspace which I can factorize. And this subspace is entirely contractive, because it's entirely contained in the contractive subspace TD. You understand the point? So cooking the cake is the following. So you take a network, you consider the Laplacian, you extract the eigenvalues, you order in size the eigenvalues, you extract the eigenvectors, you calculate the matrices E lambda I and the sequence of matrices Sn. And you start inspecting the matrices Xn in the same order with which the Laplacian eigenvalues crosses the critical point. n minus 1, n minus 2, 2, 1. And then you look for entries which are equal to 2. When you see an entry equal to 2, means that these two specific nodes, or many specific nodes, form a cluster which can be synchronized. And you have exactly the value of the threshold for which, the coupling strength for which you will have this specific cluster stable. So when for the first time in the sequence, you find an entry or multiple entries equal to 2, you make a prediction that an event will occur in the transition. The cluster formed by the nodes with labels equal to those of the founded entries will synchronize at the coupling strength nu star divided lambda p, which is the p value for which the first time you obtain this. So when you run and inspect all the SN metrics, you reconstruct entirely the transition, and uniquely and universally, because this does not depend on the dynamics. It depends only under the approximation made at the very beginning on the Laplacian eigenvalues and eigenvectors. So let me make an example, because I have only a few minutes left. I want to illustrate this because you understand the power of this. So we take this network, which is an all-to-all connected, but is weighted. So we constructed artificially these three clusters, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, by putting the weights in a way that you have this dynamical equitability. You see, for example, these nodes 7, 8, 9, 10 are equally connected to the rest. 10 to 2 is 0, 1, 2 to 7 is 0, 1. So you have this set. Calculate the Laplacian, and you now inspect the SN matrices. You have 10 matrices because you have 10 nodes. S10, do you see anything equal to 2 here? No. S9, do you see anything equal to 2 here? No. S8, wow. The first prediction is that when D will be equal to nu star divided 6003, the first cluster you will observe is formed by 7, 8, 9, and 10. Then you continue. S7, do you see any additional 2? No. It's S6, no additional 2. Here you start to see something very similar to 2. Then S5, wow. Second prediction, the second event that will take place in this transition is that node 4, 5, and 6 will join the cluster formed by 7, 8, 9, and 10 at nu critical divided by 4003. Then S4, nothing. S3, nothing. S2, you have the solid phase. Nu critical divided lambda 2, class 2. Everything is synchronized. So the transition that you can predict completely without even running your system is, and it's independent, as you will see from the dynamical system, is you first see this cluster, then this other cluster joins this, and then at lambda 2, everything joins. Then what you do, you simulate Lorentz, you simulate Rössler, two different systems. Of course, you have two different values of lambda, of nu star, because this depends on the system, but you have exactly the same sequence. These are the synchronization error of each one of the cluster, the yellow cluster, the brown, and the red. And you see, first you have 10, 9, 8, 7 as predicted, exactly at the value of D1 that you calculated. D2 exactly you have the merging, and finally D3. And if you look, this axis is nothing but this axis divided by this and multiplied by this. So it's a universal transition. It just you have to rescale the axis properly. You know, so this is twice this. This is twice this. So independently on the specific dynamical system you are going, and this is the strongest part, you will always see the same sequence of synchronization, of clusters in the synchronization. And this sequence entirely depends on the structure and entirely depends on the Laplacian dynamics, on the Laplacian spectrum. Of course, you can have much more complicated clustering structure, larger network, 10,000 nodes with 4 clusters of different sites, and the order is exactly taken. These are D1, D2, D3, D4 are the predicted values of coupling strength at which you should see that specific cluster to appear. And then is what you have when you simulate. The synchronization error goes to 0 exactly there. Now you can do, of course, with real network. You take, for example, in this case, we have taken the power grid of the United States. It's a real network made of 4,941 nodes with 6,594 links. You run the SN sequences. You predict that the transition will be made through a sequence of 381 clusters. I cannot now show for you 381 lines of synchronization error, but I selected 6. I calculated D1, D2, D3, D4, D5, D6 for the Rössler oscillator. I put here D1, D2, D3, D4, D5, D6, and this cluster goes to 0 exactly in this position. Then you say, okay, this is homogeneous case. That is the case under which all the network is made by identical units. Will the same sequence of cluster be maintained when you have variability, you have heterogeneity in the network? So you take a parameter of the Rössler, you give a variability, 10%, 5%. So now the units are not anymore identical. And if they're not identical, you know, basically the entire treatment is not rigorous because the synchronous solution does not exist, blah, blah, blah. But what I'm going to say that if I report again D1, D2, D3, D4, D5, and D6, which are the same value here, that I just obtained by the structure, so nothing to have with the dynamics, of course, now these are not good prediction because the synchronization error goes to 0 in different position, but the sequence remains. So the yellow goes to 0 before the orange. The orange goes to 0 before the red. The red goes to 0 before the violet. The violet goes to 0 before the dark violet, and so on. So in a sense, almost when also when the systems are slightly non-identical, that is, you have a parameter variation, like in normal cases, inspection of the spectrum and the localized blocks of the spectrums by means of the SN matrices gives you hints on the sequence of clusters that you see during the transition to synchronization. So I end up here because it's already time. Want to thank you for your patience and want to invite you to submit your best papers to Chaos Odds and Fractals. It's a journal where I am editor-in-chief, and there are many, many people which are editor also in the Brazilian community. I see that 2 of the organizers of this conference are editors, Yamir and Francisco, and many others are associate editor. The journal is having a great success. We have an impact factor around 8. And this year, the site score tracker is 13.2, so it's very, very large. We are #1 journal in the world in the category Mathematics Interdisciplinary Application. We are #1 in the world for mathematical physics, #3 in the world for statistical and nonlinear physics, #5 in general mathematics, #12 in applied mathematics, #16 in general physics and astronomy, and I can continue here. We are very, very top on all, Q1 everywhere, and very top on each one of the categories. We are having more than 6,000 papers submitted per year and about 1,000 papers published. So it means the acceptance rate is very low. We are very selective. And this year we had another record, which is we had more than 1 million downloads per year in our webpage of contents in our webpage. So this is really great. Not a lot of journal can have this record. And so I hope that this journal will be seen by you also as a further possibility to diffuse and disseminate your research in our community. Thank you a lot. I'm opening the journal to the talks to questions.
Thank you very much, Stefano, for a beautiful talk. Questions?
Oh,
Hello? Yes, come here. So, go to the center, please. So he sees you.
Hello.
hello.
Hello. Yeah. So thank you very much for your talk. It's actually really nice, and I'm sorry if I don't know how to formulate well my questions. So I'm Rodrigo Corder. I'm professor of parasitology, but I was interested in dynamical systems and synchronization of networks. So recently we studied like maps that are sometimes called Bernoulli maps or discrete time Kuramoto models. And we studied these in heterogeneous networks. And we saw that we also studied the transition between asynchronous to synchrony. And we saw that the synchronization actually starts, in our case, with highly connected nodes, and then slowly the cluster of synchronization moves to less connected nodes until it reaches some stable cluster that will remain synchronized. The way you showed us that you are finding the clusters and then you are changing your coupling and seeing other clusters, do you see something similar in your systems in the sense that highly connected nodes spark the synchronization and eventually you have you have a cluster with middle connected nodes when it is in when it reaches stability? Thank you.
Okay, thank you a lot for the question. First of all, if you study discrete systems like maps, the situation is slightly different in the sense that since the beginning, I'm considering continuous systems in time. It can be formulated very similar things for maps, but there are few details which are different. What I want to say is that what I presented since the beginning is ordinary differential equations. So not maps, but flows, okay? I repeat, everything can be formulated from maps because at the end there is simple derivation of one to the other framework, but there is some technical details that I have no time here to describe. But you obtain also a criteria there to have the transition and to describe the transition. What is important here is this point, which really differentiate cluster from the rest. The condition of spectral block, which is fundamentally the condition, you see, does not put any condition on the inside clustering, on the inside connectivity. So, in principle, the degree of a node is the sum of the number of connections the node form inside the cluster, okay, plus the other one that forms outside the cluster. So we do not put any condition on K in. However, K out is very important because we can prove that the stability of such clusters depends on the sub-Laplacian of their connection minus in the diagonally the total strength with which such nodes are connected with the rest of the network. So if you have a very high degree node, okay, which has many connection outside and little connection inside, this cluster with such characteristic may have very strong stability. So you may observe it before. Okay, but I repeat, there is not such a direct consequence because you can, I mean, the part of the degree that is the inside degree is not considered here. And this makes all the difference with symmetry because a symmetry orbit is a sort of permutation of the entire network, of the labels of the entire network. And here you may have also clusters which do not correspond to symmetry orbits. So it's a little bit more complicated.
Any other question? Yeah, please come. If there is any other question, be prepared to stand up.
Hi, Stefano. This is Marcos Aguiar here. Nice.
Hi, Marcos.
Hey, hi, how are you? It's a pity you couldn't come. Maybe next time. Yeah. So
Sure.
So my question is, in the examples that you showed us, you have this first cluster that synchronizes, and then the second cluster merges with the first cluster, and then the third one follows up. Can you have two clusters synchronized but independently? Or is it always like that, that you have the first cluster and the other clusters are synchronized, they merge with the ones that are already there? Can you have two independent?
Very good question.
Yeah. Okay.
Very good question, Marcus. Thank you a lot. You can have both things. You can predict the events forming the synchronization, and the event may correspond to either the formation of independent clusters, that is, group of nodes, two different group of nodes. Inside these two groups of nodes, you have two different synchronous dynamics, or the merging of one cluster to another. For example, in the case I considered, look what happened from S7. S7, you have the first cluster, okay? Then in F6, you have almost the second cluster here. But you see, this is not block, it's not everything two, it's two different blocks.
Okay.
But unfortunately, this is not sufficient because this is not two. So there is some extra small component outside, which when they merge, they merge. So that is a specific case. You can have 4, 5, and 6 forming a first block, then 7, 8, 9, 10 forming a second block, and something different than 2 in the middle here. Then you have two different clusters.
Right, so that can happen.
And this is exactly, we see this, for example, in the power grid of the United States. In the power grid of the United States, you know, there is here, of course, a geographical embedding, no, because the power grid are geographically located in different positions of the United States. So there is not a direct link from a power grid in California and another power grid in Vermont. You can imagine, because so they are locally, and so when you see different clusters, one in Wyoming, for example, and one in Arizona, and they are synchronous independent.
Right. Okay. Yeah. Okay. Thank you. Thank you.
Okay, thank you. May I continue essentially? May I continue the discussion that Marcus was started? If you consider, I mean, I'm worried about this heterogeneity or no heterogeneity of the system that you ask. Let me consider two simple cases. Locally coupled Kuramoto models, one with equally spaced natural frequencies, and the other with random natural frequencies, or, well, yes, random, separately anyway. So the equally spaced natural system is natural frequencies is well known. It was done by several people, I guess, but the best known is Pazot and other people.
It's explosive.
Sorry?
No cluster.
I see.
Explosive, no cluster.
It was done by Pazot, Diego Pazot.
Yes, Diego Pazot is explosive synchronization, no clusters. You don't have clusters.
Yeah, but wait a second. That's where we go. The point to us, if you, do you see the blackboard?
Yes,
Yes.
no, not.
Probably I have to go.
No, let me stop the sharing, then I see.
Okay. So then if you see this, what Diego Pascual had was equally spaced frequencies.
Mhm.
And if you plot here the frequencies at infinity, what he saw was things like this. Let's say all equal, all parallel, and then suddenly they all did like that, and they all met at the same point and synchronized.
Yes.
That's what he saw. So essentially, always the same system. Then, if you look at a random case, what many people have seen is the following. You have any frequency, some very separated, and then they start going like this, and they could be together, but that's another problem. And then it goes further, and this one meet to see this, and this meet with that, and then probably they all go there, and they meet like this. So essentially, these two problems, the heterogeneity of the Kuramoto is given by the frequencies, by the
Yeah, but
natural frequencies. So,
sorry,
and these two yeah.
Hilda. In
Tell
the
me.
first case, you consider locally coupled or globally coupled?
Uh,
Because in the case of Diego Passo is locally coupled.
It's locally, yeah, this is local also.
Ah,
This is
also
one
local.
local, a ring. A ring. In both
Mhm.
cases, a ring locally coupled. So, and these are the same. I mean, even you take a locally coupled and you, for instance, change this, the thing that is being called the tree of synchronization is,
No, I understand.
slightly different.
Look, the only answer I have is that
Yeah, what is,
I, my results are
yes.
formally valid under an approximation and under the main assumption that the system is identical. Kuramoto is not identical because you have different frequencies. Now, in the case of Pazot, it's clear that not only is non-identical, but is not even nearly identical, because I mean you have a connection between the first and the ends in the ring, which have a very far away frequency. Correct?
What the paso is,
In the case of Pazot, in the case of a random, it's the same problem. You cannot. You need to have a very small deviation in frequencies in order to try applying something similar to my concept. Otherwise, normally what you can have is then the dynamics start to be important. Is not everything reducible to the structure, as I'm saying, and then the dynamics starts to be important. Therefore, one, for example, start to have nucleation of cluster between um, those oscillators which have closer natural frequencies. And then this cluster reinforce itself and start attracting other oscillators to it. But this is something that depends on the dynamics, not anymore on the structure. And this depends on the fact that in both cases that you have shown here, you have a very heterogeneous system because you have nodes which have parameters, one being very far away from the other. And you cannot, therefore, imagine to describe this as synchronization of identical systems or nearly identical systems.
yeah. Yeah, okay. Okay, thank you very much. Any other question? Yes, please come.
Hello, thank you for your presentation. My name is Armando Abrantes. I'm from the graduate program of electrical engineering here in Brazil, in Federal University of Campina Grande, Paraíba. And my question is about the modeling of the power grid, of the US power grid. If you have considered all the nodes, all the generation units in your network as they were all connected. Because in fact, we have like three regions, which is the Western, Eastern, in the Texas grid, which they are not exactly connected in terms of the synchrony. Actually, they have tried to operate the whole grid of US in the 70s, but they could not keep the synchrony. So my question is if it is in your study, you have considered the US grid as a whole, or if you have considered these three small pieces and eventually they share power, and you should consider some kind of connection between these three areas.
The answer is we consider the entire grid as in the case, and we didn't do this refinement, and obviously we can do. And I think for each one of the sub part of the grid, you will have their own cluster and so on. Yes,
Okay,
it's
that's
possible.
okay.
Thank you.
Thank you.
But what I want to add is that this does not depend on the model or the specific model, because everything under the assumption of identical system depends on the structure. So you can have there Rössler, you can have there or the second order Kuramoto, as normally is done with power grids, and you will obtain exactly the same sequence of clusters. So what is important in the studies, of course, under important assumption, the first, identical or nearly identical systems, and second, that you refer always to a unique solution. These are the two assumptions. Then you can demonstrate that you can again separate structure and dynamics, and the entire transition to synchronization under this assumption is entirely and universally described by the structure of the network.
Okay.
So
yeah.
you don't need to make any simulation. You just take the network structure and you obtain all the transition from there.
My point about this refinement, as you said, is just because as you consider like this technical characteristics of the network, which is divided in three units, you change the topology by itself because.
Okay, so if
have
you change the topology, then it will change also the sequence of clusters.
My point is, considering this technical, I would say, refinement would probably just change the sequences of the nodes or maybe this cluster. But in fact, we have another network because there are this specification on the network. When you really see the real network to construct your abstraction as a complex network.
Look, I'm not an expert in this field. You come from electrical engineering, so you are much more expert than me on power grids. If you want, I will be very happy to apply this method, which is so simple. It's just constructing a sequence of matrices and inspecting them on the data you have. So write me please an email. My email is stefano.boccaletti@gmail.com.
Okay.
So my name dot my surname @gmail.com, and I will be very, very happy to interact.
Very nice. I'll do that. Thank you.
Thank you.
Well, any more questions? Well, thank you, Stefano, for a great talk and for having solved our problem.
No, it's my pleasure to be there. And it's not my pleasure because, well, it's my pleasure to be here. Thank you a lot. Thank you, Hilda, and all the others. And wish the success of the conference, I'm sure it will be. And also success of the dinner of the day after tomorrow, or the day of tomorrow. Sorry, tomorrow. There is a dinner, no? So there I will not be able to eat asado or churrasco.
Okay. Bye-bye. Thank you very much.
Bye-bye.